Okay, today I want to talk about heat and magnetism. Now, some people have said that I don't seem to understand that if you heat up a magnet it loses all magnetism. Well, I do. I've said since the beginning that all atoms are magnets. Atoms act like magnets. And magnets act like atoms. As in, you can stick magnets together, and depending on how strong the magnet is, how much energy you have to use to pull two magnets apart, okay? It's the energy involved that pulls the magnets apart by your energy, okay? So energy separates magnets. So let's look at heat and magnetism. Tesla did it, several other people have done it, millions of people know that magnetism and heat, you lose all magnetism when you have heat. Well, let me just show you what I understand, knowing that all atoms are magnets. This is how water is formed. Now, I was watching a video the other day just to make sure. It's a very informative video, and I've put the link in the description at the bottom. You can go and watch that, and it confirms everything I'm about to tell you. Alright, that's oxygen. That's hydrogen. Now, hydrogen travels around in pairs. Oxygen travels around on its own. Now, when water is formed, oxygen and water come together, and it doesn't take both of them equals H2O. Nope. The oxygen does not take both of these hydrogens and form water. No, that's not what happens. Apparently this is called a free radical. I might be slightly wrong about the name of it, but just for these purposes, that's a free radical and these are free radicals. And when these meet, when H2 meets O, what actually happens is that OH. Then this free radical, and what comes off of this obviously is H, and then this free radical and this free radical, they float off. This one floats over here until, of course, it meets another free radical of H2, and then the hydrogen is taken, which gives us a H free radical and H2O. Now we have water. Yes, that is how water is formed. How many rotations do I say is on an atom or a planet? 2. There's only clockwise plus counterclockwise. So, I can easily say that the oxygen took, let's call that, clockwise. It took the clockwise. Can't deal with the counterclockwise. But why? Unless, of course, these are both clockwise. Or these two over here are both counterclockwise. But what it does is, so there must be either, you have to keep up here because this is going to be good, clockwise and clockwise, or clockwise and counterclockwise. Do you see what I mean? So there's a difference here. There's probably 2 more, might even be counterclockwise, and counterclockwise, and counterclockwise, and clockwise. But the oxygen molecule has 2 vortices, and it's taking either clockwise or counterclockwise, and then it's making either clockwise and clockwise, or counterclockwise and counterclockwise, or clockwise and counterclockwise, or counterclockwise and clockwise. So eventually, you know, science could figure this out from what I'm doing here. But I've said that, you know, out of a magnet is two vortices, clockwise and counterclockwise, between the inertial plane. Okay, so you have that on either side of a magnet, and so I'm saying you have that on either side of an oxygen molecule, because why else would it not take this free radical here? This is H2. Taking it to H2O would be very, very simple, unless, of course, the mechanics, the physical mechanics of attachment, the same as this, will not take a clockwise here. These push against each other in a magnet. So one of these doesn't fit either side of this, which is why I said it's either clockwise and clockwise, or counterclockwise and counterclockwise, or a strange mix of both. So we could sit here, because this can't be counterclockwise, because this side should be counterclockwise. But if this is clockwise and clockwise, it will never accept counterclockwise. Now this could be clockwise and clockwise, and this is clockwise and counterclockwise, but we only ever have two choices, which may add up to 4. So the fact that this H2 and this O do not become H2O, means that the rotational vortice that is coming out of this does not grab hold of that one. So this one has to move over here to a different set of H2 radicals, pick up the opposite side, and become H2O. Okay, and it's all based upon the rotational system around the oxygen magnet, the same way a magnet will only attract another magnet depending upon the rotation that you put to it. Clockwise accepts counterclockwise, counterclockwise accepts clockwise. So this is either neither, or it's two of each, clockwise and clockwise, or counterclockwise and counterclockwise. It would be very simple to work out if, you know, we really wanted to get into it. But that's as much as I can kind of tell you about this, because apparently I don't know anything about physics. But yeah, so the oxygen won't immediately pick up two H2. It will take one of them, it will move to another, it will get that. You get water. Okay, so that's how you make water. It's very, very simple. We just have to figure out, is it clockwise and clockwise, and counterclockwise, and so on. Now, let's come to the name of the paper. Heat and magnetism. We all know that magnetism fails when you add heat. Why would that be? Well, here's a very simple analogy. Water is H2O. That is a magnet arrangement. Okay? It is one thing with two things attached by a vortice arrangement, which if we had another magnet here and another magnet here, it'd be exactly the same. Now, if we heat up the water, what happens to the molecular bonds of H2O? They say, see you later, and they all fly off into H and HO and H2 and O. Basically, when you heat up the oxygen magnet, it loses all magnetism and turns into steam. And that is why all atoms are magnets, and all magnets act like atoms, because this does the same as water. So if we take the most basic magnet around, which would be, let's just call it oxygen. Well, how do you break the magnetic bond between oxygen and hydrogen? Well, you add energy. Okay, so to pull apart two magnets, I add my energy to separate them. What do we do to water to get it to separate into its constitutional parts? We add heat, 100 degrees of it, Celsius, and that changes this magnet into basically an energy bomb, and everything is going one way. It is no longer accepting energy, which would go that way, which would mean oxygen and hydrogen would wind together and pull in to form a greater mass. It now has so much energy, this mass now inflates. and so your magnetism is gone, and now you just have steam. And then when the heat dissipates, you get water, and the magnets reassert themselves, the same as any magnet that you heat up, and when it cools down, it's a magnet again. So a magnet is not actually a magnet, because every single atom in the universe is a magnet. Atoms are magnets, and basically, as you've just seen, they work exactly the same way. So heat and magnetism, there is no crazy magical thing about it, because oxygen is the magnet here, and hydrogen, they've just stuck themselves together, 3 magnets. You add heat and they all move apart because they all have too much energy, and so the magnetism is lost, or even compressed into forcing everything out. But magnetism, it no longer acts as a magnet because it has too much energy, and so basically the atoms just spin off. They rotate against each other and pull away. Basically like 2 rockets forcing against each other, which is the only way you get movement in space, but it's that way. So there we go. Heat and magnetism, quite easily explained using the analogy of water molecules and what happens when you add heat, because magnetism doesn't exist. There's no such thing as a magnet. There's only atoms that focus energy, which is why now we can make magnets. Certain combinations of materials, cobalts and neodymium, when you put them together they make a greater magnet. So iron becomes magnetized and pulls iron into itself. Is it difficult to pull apart? Not if it's dust. But different magnets attract different things, and each one of these, every atom is a magnet that attracts not iron, but it might attract hydrogen, and hydrogen attracts oxygen. Do you see? All atoms are magnets for other magnets, other periodic table chemicals. And that's how heat and magnetism works. I'm sorry it sounded really boring, but I didn't want to mess it up too bad. So, heat and magnetism, why does it happen? Now you know I know pretty much all about heat and magnetism and why it loses its magnetism, because there isn't any such thing as magnetism. There is only energy flow, in or out. No such thing as magnetism, because all atoms are magnets. And the sooner people understand that, the easier life will be. Energy and matter are separate. Energy attracts matter, matter covers energy, and energy moves matter. No such thing as a magnet. Thanks very much. My name is Lee. I follow the Christ, and I tell you things when he shows me what they are. So, September, I don't know, 30th, let's say. It's Friday. Woohoo! And I'm off. Early week. So there we go. I hope I made that plain. All atoms are magnets, and all magnets act like atoms. Water is a magnet, a set of magnets that when you apply heat to it, it loses all magnetism and turns into steam. And then when the heat, magnetism, extra heat is energy is lost, it turns back into its magnety self. Thanks very much. Bye.